So there is a the other relation one can derive from this is that actually theorem one doesn't write, we can show, but so we can show the theorem that for an irreducible representation the sum of the character square in any representation is equal to the order of the G, order G. Now this comes out because, so proof we had this relation earlier that chi d is therefore mod chi d squared and summed over G will be equal to sum over alpha, beta as well as G. So when we want to do mod square, we have to write this sum and we have to write square star of this sum multiplying it. We just put different summation indices alpha and beta in the two. So we will get m alpha chi alpha G times m beta chi beta star G, right, and the sum now is over alpha beta as well as G. But now we can exhaust the G sum by just focusing on the chi alpha chi star beta. That produces for us a delta alpha beta so that collapses this sum to just being sum over mod m alpha square. And then there is a constant factor which is order of the group. But now you specialize chi d to be any favorite representation you have, then irrep we basically get that because then there is only one m alpha which is non-zero. So that implies this, but I will write down we can rewrite this as sum over classes also. Chi alpha I, not yeah, squared equal to G. So those are all very interesting restrictions because eventually you want to know all these characters for any representation, because you can analyze the small vibrational modes of a molecule by its symmetry group. Knowing the symmetry group, you can classify the vibrations into different conjugacy classes, and you want to know their characters. So this puts restrictions on what kind of character table you can have. Okay, so I think this is how much we are going to do in terms of formal stuff. The next thing is to introduce what is called a regular representation, because that is an important construct. And for this I wanted to refer to this textbook of Dresselhaus. I don't know whether I can get to it. In any case, I have the notes written here, so I can do that as well. But so the idea of a regular representation is that you treat the group elements themselves as the carrier space. It's quite amusing, isn't it? How much you can do with itself as the carrier space, and represent elements as permutations depending on how left action of that element permutes the rest of the group elements. Okay, so this is action of group on itself, left action, and we know that left action will reshuffle the order of the elements, so it is essentially a permutation. And anyway, we know any finite group is subgroup of the permutation group, so we are not surprised that it is a permutation. So we represent them as permutations, and so we make the rule that G, which is the action of some element Gi on right. So we treat these as essentially components. So representation D, or how should I write this? I have used here R. So R is a matrix representation of Gi acting on components x1, x2, xm, where actually m is the order of the group. So there are as many components as there are group elements. So essentially, once you treat G itself as the carrier space, it is a m or mod G dimensional vector space, and the xi are the components in it. So we define this operation as being equal to x and then pi I of 1, x pi I of 2. So we permute the elements, we permute the components such that component number 1 goes to whatever the fate of group element G1 was under left action of Gi. That's roughly what we are saying. And what happens in such a representation is that thus we get m by m, well, which is same as, just not to get lost, size of G by G represent matrices, or a representation of dimension G. We don't write the G cross G, right? When we say matrix of representation of dimension G, means the corresponding matrices are G by G. So this representation is somewhat bloated, it is highly reducible. In particular, you will find that the character of none of the elements, character of every single element is 0 in such a rep, except identity. So we write this D without any brackets or label for meaning the, I could also have written chi R maybe. Okay, chi character in regular representation R for any element G is equal to 0 unless, so or except chi R of the identity element. The identity element has always to be represented by the identity matrix in linear algebra. So that can't be, that trace can't be 0, and it has to exactly tally the dimension of the representation, but the dimension is itself G. Now this can be also used to prove an important result, that in this reducible representation any particular irrep is contained exactly exactly as many times as the dimension of that representation. Actually, I should have gone on to that. I hope it's not becoming all too abstract, because this book has a nice example. Okay, so let me do the following. I say this and then we do the example and postpone the proof. So we can show, so we can write chi R of G equal to sum over alpha m alpha chi alpha of G as before, and find that m alpha equal to n alpha, the dimension of irrep alpha, and hence we can prove that so regular representations. Now this book has a nice proposal how to find a regular representation. To find it is usually a little cumbersome, because technically you have to start with, you have to fill out this table where you have to check, you take a particular element G, start acting on it, acting with it on all the other elements, and then see where it sends each of the elements, and then you have to fill out this matrix. So this book suggests a recipe for finding the regular representation. Regular representation is found directly from the multiplication table by rearranging the rows and columns so that the identity element is always along the diagonal. Okay, so you know that you do this write out multiplication table, identity can occur wherever the inverse occurs. But now you rearrange the table such that the rows and columns, so that identity comes exactly along the diagonal. When this is done, the group elements label the columns and their inverses will label the rows, and we will illustrate this permutation group of with permutation group of 3 objects, which is S3, what we have been writing, for which multiplication table is given in 1.1. Application of the rearrangement theorem to give identity element along the main diagonal gives table 3.3. So yeah, this is the table 3.3. Here this is just the equilateral triangle, its rotations and it flips, and E is identity. A and B are the 120 and 240 rotations, and these are the, sorry? Yes, so C, D, E are the flipped rotations where you change the signs of either one top row or left column. So these are one conjugacy class and these are one conjugacy class, and this is E is conjugacy class by itself. So first of all, they are pointing out that this is the multiplication table. So they have rearranged the multiplication table so that E is I'm not pointing there, okay. So yeah, so E is along the identity, right, that along the diagonal. Then the statement says after you do this rearrangement, what you have to do is, then the matrix representation for an element X in the regular representation is obtained by putting 1 wherever X appears in this multiplication table. So if you want, say, A the basic rotation first, then you put 1 here and you put 1 here, you put 1 here, 1 here, 1 here, 1 here, and that's all. Okay, so that will be the matrix for representing A, and so on. So you now, for any given element, like to produce C, you put 1 here, you put 1 here, you put 1 here, wherever you see the C. First thing you can see right away is that the character of any arbitrary group element will be 0, because you will never get it on the diagonal. Only the identity element will be on the diagonal. So they are writing, for example, for A in regular representation, it will look like this, 1 and 1 there, and like we had identified the rows and columns. So by construction, only the dereg of E has non-zero trace. Now we show that the regular representation is indeed that they are trying to check. That's not too much of a surprise, one can check that. I wanted to get to the detailed example on triangle. So they are actually going through the proof of the fact that this actually is a homomorphism and that it will work as a representation. So then the theorem that regular representation contains each irreducible representation a number of times equal to the dimensionality of the representation, the theorem I stated. But what I wanted to show was this recipe of how to generate the regular representation for a particular group. So using this, you can, this trick of rearranging the table until you get everything on the diagonal, that rearranges, of course, how the the important thing to remember is that it is no longer the multiplication table, it is a rearranged table where you can see the first entries. Here the entry is EABCFD, whereas here is it EABC and then DF. So the rows and columns are not now labeled by exactly same thing. Rows are labeled by inverses and columns are labeled by the elements, but that puts E along the diagonal. Okay, so I think we will stop here today. We have proved quite a lot of things, and using these results we can actually begin to, yes, I had a, actually I thought that they gave the matrix example, but we will continue next time.